Okay, so what we've done in the last week, right? Redox reactions, electron transfer, reduction oxidation, reducing and oxidizing agents, and using oxidation numbers. Balancing of half equations, balancing ionic equations, including states for overall redox reactions, and cohes, right? What sort of conditions can we apply cohes in? Acidic only, that's correct. Cool. All right, and so this is what we're moving on to today. Galvanic cells as primary cells. We'll talk about the definition of what that means, and as portable or fixed chemical energy storage. Right, so it's an extension on from this idea of fuel. So fuel is stored energy that can be then converted into heat or work, right? So if a battery or a primary cell can convert the chemical energy into electrical energy for us to be able to use for something. Produce electricity. Details of specific cells not required. So for example, I've got an example of the Daniell cell in this presentation. You're not required to know what the Daniell cell is. Right? It's about application of your understanding, not about specific examples. Right? What we need to know is common design features. Anode, cathode, electrolytes, salt bridge, separation of half cells, chemical processes, including electron and ion flows, half equations and overall equations. So there's a lot of detail in a galvanic cell, and it counts for a good 5+ marks on a test or an examination. So let's have a look at a typical galvanic cell here. We had in your holiday work, this looks slightly different. So this looked a bit like this. Right, so when we use gaseous reactants, right, we're going to use a platinum electrode. So I'll just do that. If I make that larger, right, so hopefully the recording of this can see what I'm doing on the board. Right, let's zoom this way. Okay. Right, zooming in there. So we've got gas coming in here, chlorine gas, right? And so I'm labeling these components. This is a platinum electrode. Chlorine gas is going in here. This side had lead in a lead solution, and this would be chloride ions in solution. Okay, what's the purpose of using an inert electrode? Why would we use an inert electrode? Right, doesn't interfere with the reaction. Why do we not have an inert electrode this side? Right, we want lead to be part of the reaction. Yeah? If I just bubble chlorine into the water, nothing's really going to happen, or it's going to react with the water. The purpose of an electrode is what? What's the purpose of an electrode? Right, exactly right. It is the site at which the electrons transfer, right? So we need a surface. And something about inert electrodes is that they are porous. Why might they be porous? Fantastic. Increase our surface area to volume ratio. It means that gas more easily diffuses through the porous electrode. Right. So far, I've got the components. There's other bits that are missing. An Euler-Rigel cat. So we need to determine which is the anode. Oxidation always occurs at the anode. No exceptions. Right? So many exceptions in chemistry. This is one where there's not an exception. Right. Look at our periodic table. Switching back to here. Let's look at, not periodic table, sorry. Let's looking at our electrochemical series. Here. Looking at electrochemical series, we identify where's lead. Lead is, getting my laser, right? Lead is here. So there's lead. Yeah. And where is chlorine? Chlorine's up here. So chlorine gas is a stronger oxidizing agent than lead ions, so it will reduce. Lead solid is a stronger reducing agent than chloride ions, so it will oxidize. So we're going to have lead oxidizing. And we're going to have chlorine gas reducing. So this is our oxidation reaction. This is our reduction reaction. Switch back to that. Okay. So oxidation, reduction, I can do my overall by adding the two together. Gives me lead solid plus chlorine gas. Gives me lead 2 plus aqueous plus 2 Cl minus aqueous. Right. Still have some more details. I need to label anode. This is the oxidation reaction, so this is the anode. This is the reduction reaction, so therefore this side is the cathode. In a galvanic cell, the anode is the negative terminal. Cathode is the positive terminal. Yeah. Sometimes it's referred to as what's the polarity of the half cell, or what's the polarity of the terminal, negative or positive. Two more bits of information we need. We need the flow of electrons. Where do electrons go? Correct. Where? How? Where do I put it? Right, through the conducting wire. Here's the electron flow. So electrons flow from anode to cathode via the external circuit. So we call this the external circuit, and this is called the internal circuit. Right. One thing I'm really happy that you didn't say is it wasn't left to right. Yeah? Because I could have illustrated the lead on this side. So it's anode to cathode via the external circuit. So, what's the purpose of the salt bridge? Something about neutral. There's a particular word that's missing. Electrical, right? Maintaining electrical neutrality. So, let's say I've got potassium nitrate as my salt bridge. So electrons going in this direction. I want the anion to continue in the same direction. Yeah? Flow of negative charge. Electrons via the outside, the anion continues in that same direction. Therefore, to balance that charge out, the cation moves towards the cathode. Yeah? Right. So salt bridge. And there's all my key components. So these solutions are our electrolyte, right, and so on. Switch back. Yeah, and go back. Okay. Comparison of energy transformations occurring in spontaneous exothermic redox reactions. So if we have the slide, yeah, stronger oxidizing agent, stronger reducing agent. If it slides, it's spontaneous. Yeah? If we have to walk up the slide, it's not spontaneous. Yeah? What did you learn as your mnemonic device last year? Backward C, slide, different ways of remembering it. So if it's spontaneous, it's exothermic. So we've got some heat being released. If we're having to put energy into the system, then it's endothermic. So recharging your batteries, putting your phone on charge, is an endothermic process. Even though it feels like your battery is getting warmer rather than cooler, it's still endothermic because you're pushing energy into the system. It gets warm because there's a bit of resistance there, right? And we'll get to, it's called a secondary cell, things that are able to recharge. And in order to recharge them, we need to do greater than the potential difference. Use of electrochemical series in designing, constructing galvanic cells, etc. So we'll get to that. Here's our key terms. Is there anything in there that you've never seen before? So what's electromotive force? Anyone seen that? No idea? What's potential difference? Have you seen that? Right, in terms of the E naught of the half cell from our electrochemical series, yeah, the difference between the two E naught values is our potential difference. Electromotive force is just the same thing, different way to describe the same thing. Because voltage, right, is the force in which their current flows through a circuit. Standard hydrogen half cell, standard electrode potentials, E naught, primary and secondary cell we'll get to later. Galvanic cell, nothing new here. We've talked about these issues. Electrode, site of redox to occur. Electrolyte is the solution that contains ions. Right? What do we know about electrical conductivity? We need to have free moving charged particles. If we don't have free moving charged particles, electricity won't flow. Half cells, why must they be separate? Exactly, right? We're going to have a direct transfer of electrons from, let's say, if I bubbled chlorine and had the lead sitting there rather than platinum, I'm not controlling the electron flow. In order to get the advantage of the electricity, I need to separate the half cells so that I'm capturing the electron flow. It's like one of the, in the early emergence of solar technology, that's exactly what we're doing. We're trying to capture and slow down the electron transfer. Internal circuit, talked about that. External circuit, internal circuit. Salt bridge. What are some issues with the salt bridge that you could tell me? What may occur with the salt bridge? Runs out of what? Ions. Right. So if all the ions have migrated, I'm left with essentially water. Water's a non-charged particle, no longer flows of electricity. Alternative, it may dry out. Same issue, right? If the water dries out and left with just salt, then there's no flow of ions because the ions are no longer in an aqueous state. Observationally, what would we see in this half cell? This side. What are we going to see? Any guesses? What's happening with the lead? Right. It's going to break apart. It's oxidizing. What are we going to notice about the voltage? Over time. What do we expect? It's going to drop. Yeah, so our voltage is going to decrease as this continues to oxidize. We're going to see a mass loss in this reaction. Yeah? So in the event when I've got two reactive electrodes, yeah, the reactive electrode at the anode will always decrease in mass. We're not going to see an increase in mass on this side. Why? Because I'm not reducing an ion to a solid that's depositing onto the electrode, but rather I'm reducing the gas that's going into solution. So no mass change here. Other examples. Half cells, electrochemical series, blah, blah, blah. My main comment in one of the questions, I forget what page it was on in your holiday homework, was this idea that making explicit reference to oxidizing and reducing strength when talking about why a reaction is spontaneous. So slide for spontaneous, top left, bottom right, chemical species. Got my slide, spontaneous reaction.